Hi, in this video, we want to take a look at interaction terms and linear regression. Okay, so the idea of interaction terms are that I have a predictor, I have another predictor, and then I multiply them together to get the interaction term. Now, so remember, whenever we're doing linear regression, all of our data is always numeric, some way, some shape, some form. So if I have categorical data, by default, what R is going to do is going to take the categories and it's going to make binary 0, 1, binary 0, 1 vectors that correspond to each level of the categorical variable. So if I have a 10 level categorical data, 10 level, I would have 9 dummy variables. 10 minus 1 is 9. If I have 5 levels of a categorical data, then I would have 5 minus 1, 4 dummy variables. So if I have 2 very frequent, something like male, female, yes, no, success, unsuccess, pass, fail. If I have 2 levels, then I'm going to have 1 binary vector. All right, so what we want to do, we want to take a look at interaction terms when I'm doing linear regression. And here we're going to have a numeric vector and a categorical vector. And so what ends up happening in this situation is that for the numeric vector, numeric predictor, the interaction term sets it up so that I have 2 different slopes for that predictor depending on the value of the dummy variable. Okay, now let's say I don't have interaction. What having just the binary vector in there, so it goes through without, if I don't have interaction, if I just have the categorical data, it's going to change the y-intercept. Now, if I have an interaction term, so that is categorical, multiplying by the numeric vector, then I'm going to have a different slope for each level of the categorical data. Now, if I have both the dummy variable and I have the interaction term, then I'm going to have each level of the categorical data will have its own slope and its own y-intercept. And so effectively, if I have 10 levels of my data, of my categorical data, and I have the vector and the interaction term in there, then each level effectively has its own linear model. Now, why do we do the N-1 business? Well, really, that stems back to how things were done, like back in the day. That when computer memory was more expensive, it made a lot more sense. It makes a lot of sense from the point of view of trying to keep things slimmed down inside the computer so it works more efficiently. Nowadays, really, we could get by without, but there's kind of like a historical standard. And especially if you talk to like older statisticians, this is the way they think because that's how they were trained. That's how they dealt with it. More modern points of view are we can kind of lighten up on this, but it works mathematically, algebraically. Everything is easy peasy lemon squeezy to work with on the computation fronts. The interpretation can be a little bit difficult, but we'll get to that later. All right, so in this example, we want to consider a situation where subject matter experts believe that there is a substantial difference between East and West restaurants in New York City. Okay, so much so that East and West should have different models. Okay, so different models. Like I said a moment ago, if I include the categorical predictor variable for East-West and I do an interaction term, what that will do for simple linear regression is it will set it up so that East has effectively its own model, West will have effectively its own model, even though we print it out as 1. And there's advantages and disadvantages of printing them out as 1. There's advantages and disadvantages of like separating the data and building it that way as 2 separate models. The standard is to have them together. All right, so, and this is the type of situation you actually get into when you start working with subject matter experts, a lot of times they will have like preconceived notions that they believe something to be true, and like sometimes it's just not in the data. It may be there in real life, but it's not in the data I'm working with. And if you, so then you have to make a decision on, do you talk to the person? Do you fight with the person on it? Do you know, to go with the data? Do you go with what they believe to be correct, even though what you're seeing in your diagnostics says that what they're saying is incorrect? This is something that I deal with routinely at work, is where the subject matter expert absolutely believes something to be true, but I look at the data and there's just no way they're right. My advice to you is do what people will receive. Okay, it is better to do weaker data analytics, weaker statistics that is accepted and used, than to do the best data analytics and best statistics possible and have people reject it. So just, you know, and it's really hard, you know, coming through all this math education and statistics, and like you know, I look at it, I know I'm right, but if my audience doesn't accept my results, I might as well just have not done the work. And, you know, weaker analytics is better than no analytics, you know, as long as you are providing, you know, useful information. Remember, no information is better than bad information. So don't get, if it's just bad information, just say no, just refuse. But if it's not as powerful as it could be, but they'll receive it, they'll accept it, go for it. All right, so to address this, we create two models, one with east-west as a binary predictor variable and interaction terms, and the other model excludes the interaction term. So one model, east and west, will effectively have their own slope and their own y-intercept. The other model, the reduced model, will have the east-west predictor variable, so there'll be different y-intercepts. Okay, so let's go ahead and load the data. All right, so something I did want to go through this is I set the row names to the name of the restaurant. I do that on, so row names NYC are set to the restaurants. That way, when I'm looking at the diagnostics, on the plots, I'll see the name of the restaurant rather than the row number. Now, something I do, I like to order my data by an important variable. Target variable is price. Why do I do this? Well, when I look at the Cook's distance plots, those are arranged by the order of the data. And so if I can see a trend, you know, with regard to price, or frankly, any other variable, if I see a trend in it, since it's ordered by the order of the data, I might pick up on something. I might find that there might be something going on with my data that I didn't know about previously. All right, now here what I'm going to do, since east-west is very important on this project, what I'm going to do, I'm going to go ahead, I'm going to color by east and west. So if it's east, then I'm going to say green. If it's west, I'm going to say blue. So on this logical statement, we're saying east-west equals 1. That means that the east, it's an east restaurant. All right, so a yes means it's green. No, when this is false, when this is a false statement, that means it's a west, therefore it's going to be blue. All right, so let's go ahead and explore the data with visualizations. And notice that I'm using plot character 21, and I'm putting the background to blue-green. And by default, the edge of the dot will be black. I do this to help make things pop out, make it easier to see. And we can look at the plots. And I'm not really seeing a pattern, honestly. So like looking here, I see green throughout, I see blue throughout. And so if I go along here, price is the y-axis. I don't really see like a vertical separation going on. Now here between decor and food, maybe there might be something going on, a little bit of difference. but those are predictor variables. All right, so let's go ahead and look at the box plot of price by east and west. All right, I've got blue, green. Let's see. I got my colors switched. Oh no, I'm so sorry. All right, so this is incorrect. I should switch the colors. I'm looking at these two box plots, and I see that the median lines are slicing each other's boxes. So here I'm leaning towards there's not a major difference overall. That way, this is kind of like a visual version of a t-test, a two-sample t-test. If the median boxes slice each other's boxes, then there's probably not a difference. Now, if you get enough data, a t-test will always conclude that there's a difference with very, very small differences because of the level of precision you have. But operationally, I'm not seeing a difference. All right, let's do it again. Let's look at decor by east-west. I conclude that there's no significant difference, substantial difference, operationally useful difference. All right, median lines slice each other's boxes. I conclude there's no operationally significant difference. And a little bit closer, but these are close enough that for service, I think it's probably about the same. All right, so now what we're gonna do, we're gonna build the full model. All right, so this model is given by the textbook. This is why I went with it. Because the scenario of subject matter experts is fleshed out inside the textbook. But you'll notice I've got decor, food, east, and service. Those are our numeric predictor variables. And then we have our interaction between east and service, east and food, east and decor. Okay, so what this is doing, this is categorical. So this term here says that for east and west, we'll have different y-intercepts. Now, what this does, this makes it so that east and west effectively have different service slopes. East and west have different food slopes, and east and west have different decor slopes. All right, so let's take a look. All right, so here, the slope for decor, when it's west, is 1.9. When we're talking about east, if I want the slope for the east model of decor, I have to take this value and I add it to this value. So 1.9 minus 0.3, so 1.6 is the east decor slope. Now for food, the slope for food is 1 if we're talking about west. Now the slope of food for east is 1.2. So food, that's kind of a pretty big substantial difference. So food, the slope for food on the east is 2.2, while the slope of food on the west side is just 1. Now for service, on the west side, it's 0.7, and then negative 1.3. So this is interesting. So when we're talking about on the east, in the east part of the region, we're talking about service. Better service gets lower ratings. Does that sound right? Better service gets worse ratings. Does that sound like something that, should I have that in my model? Probably not, probably not. So one of the first things we always want to do when we look at our coefficients is that we want to interpret what's going on. And so if I see, so remember, when I look at this value, this is not the value I actually care about. I care about this combined with regular service. So this is service. So what's going on is that West is like our benchmark standard reference point. When I talk about East service, I have to take this value and combine it with this one. Now, after I combine it, it's negative, which means that when I'm talking about East, the slope overall service is negative. Therefore, higher ranked service restaurants do worse than lower ranked service restaurants. Now, there might be something weird about people in the east part of the region. I don't know. Maybe it might make sense. But my knee-jerk response is that this interaction term should not be in the model. That's one of the best things you can do to check model quality is, do these coefficients make sense? If it doesn't make sense, throw it out. All right, now let's go ahead and look at multiple R squared and adjusted R squared. Remember that adjusted R squared will be smaller, only a little bit smaller. If I see a big gap between these two values, I start worrying about overfitting. So here I don't see a problem with overfitting. Now you'll notice that how I arranged the formula when I built the model was I actually ordered things so that there would be like a significance going on. So we, I did exploratory stuff before I wrote this up, but you can see that among the linear terms, here's like the order of my thing. Now East is kind of weird on this one because it's so important, so I didn't put it at the lowest. But down here, you can see that we have the lowest value at the bottom, and then these two are practically the same. So I just left service before food. Now when I look down here, remember the ANOVA table is telling us if I have decor and then I add food, this is the p-value for the hypothesis test of should I add food as a predictor to the decor model. Now this p-value is should I add East to the decor plus food model, and so on. So you can see that adding service to the decor food East is not the way to go. All right, let's do our diagnostic plots. Let's take a look. All right, so remember, when I look at residuals, I don't want to see a pattern, and I want this line to look flat, if at all possible, flat at 0. And remember, residuals will always add up to 0. And we can see that there's 3 points up at the top here that have the most extreme residuals. And we can see the same 3 points on the QQ plot are on the far right. Now we can look at the square root of the standardized residuals. Not seeing a pattern. That makes me feel good about this. And remember, I have it ordered by price. So I don't really see a pattern in these. So Cook's distance is not corresponding to the price target variable. Here we're looking at the leverage and the standardized residuals. And remember, when I look at this plot, I want to look along the contour. So the grayer the contour line, that's where I'm more concerned. So here, like that point and that point, kind of interested in. But also, these are pretty far out along their contour line. Now let's reduce the model. Now here, what we're going to do, we're going to go decor food East, and we're not going to have service. We're not going to have any interaction terms. So this is a much simpler model. And this is the model that was presented in the textbook. Let's look at this. you can see that all of them, including the intercept, are statistically significant. All right, so my personal opinion on linear regression is that when you look at the summary, it is okay to have one non-statistically significant predictor. Once you get past one, you might have some problems with some variance inflation aspect and some overfitting. I usually personally try to limit it to just one. When you start working with like actual real data, you'll find that the goal of having all of your predictors be statistically significant can be problematic, that you won't get good enough of a fit for like real life operations. So I personally limit it to one coefficient that is not statistically significant. And I find that that's actually a good rule of thumb for real world data. All right, so let's take a look at R squared and adjusted R squared. All right, they're closer together. That makes me feel better. F statistic on both models was statistically significant, but that's not surprising. It just says that the F statistic just tells you there is something in your predictors that's useful. It doesn't tell you what's useful. It doesn't tell you if there's anything that's not useful. You have to use this part to make that judgment call. Now, when I look at the analysis of variance table, everything's looking good. Now let's look at the plots. All right. I mean, kind of similar to what we got before. Now the normal QQ plot looks a lot better on the left. Still a little bit of deviation on the right, but it's not as severe visually. You know, similar output. Now this looks very different. Let's scroll up. So here we have a what, 0.14 at the top. Let's look what we had up top. Here we have 0.15, and we have like more individual data points sticking up. So if I have fewer ones with larger Cook's distance, I feel a little bit better. So here, the second and the third highest aren't as high, and the top one is lower than it was before. So I'm feeling better about this. And I think there were more points up in this region on the other one. Not a big difference. I would say it's better though. All right, now let's compare the models. So remember, what I do in ANOVA always compares models. So if I do ANOVA with one model, it's comparing it to the model that uses just the sample average as a constant. And that's the y-intercept with slope 0 for everything, for all numeric predictor variables. So if I do regular ANOVA, I take model, I compare it to sample average model. If I take two different models, it compares them, and it asks, is it worth it to have all of the other predictors? So you'll notice that here is model 1, the reduced model. Here is model 2. Okay. Well, the difference are, it's service, interaction term, interaction term, interaction term. What the F-test does for us, what ANOVA does, this asks the question, is it worth it to add on these predictor variables? So remember, the more complicated the model is, the more difficult it will be to interpret, more difficult it will be to work with. Also, I run the risk of overfitting. So the hypothesis test is that these two are informatively equal to each other. The alternative is that the second model is more informative. I look at my p-value. I conclude that the two models are equally informative. If they're equally informative, I want to go with the simpler model because that's easier for me as a human being to work with. So I conclude that the non-interaction term model is the one to go with. So the data is telling me that east and west really should not have much of a different model. They should just have different y-intercepts, and that's it. Now, when it comes to slope, they should be the same regardless of where we are geographically. All right, that's all I've got for you. Take care and goodbye.